Okay, so we'll be considering approximation of entropy. And just like we mentioned earlier, can we approximate an average value? Yeah, at least we got different views, right? So we'll now see what we can do here. So, okay. Okay. Now, if we consider entropy in terms of information theory and coding, now we can look up some concepts to be approximation of the entropy. And such concepts are the asymptotic equipartition property, and the entropy rate. Okay. And why, you know, do we want to make such an assumption? Because when we actually deal, or when we deal with a long sequence of random variables from, say, you know, a stationary stochastic process, for instance, so we now see that as they provide an estimate that is as close as possible to the average value of the information per symbol, then we could measure what the entropy is. And then we now see that one major distinction at this point is that the asymptotic equipartition property will focus on the distribution of the typical set, because we're going to see the difference between typical and atypical and atypical set. So we're going to be having two sets. Okay. So we now see that the AEP gives us an approximation close to the typical set. Okay. And then the entropy will look something like, you know, the average conditional entropy over time. Okay. This will lead towards the average conditional entropy. Okay. So the bottom line is, what are we talking about when we address these two concepts? And then what are these two concepts? Now, these two concepts are really similar in the sense that when we talk in terms of dependent variables, yes, we talk about entropy growth. Okay, this is entropy growth. Okay, but when we talk about independent and identically distributed random variables, we talk about asymptotic equipartition property. Okay, and then we now see what is a typical set. We're going to talk about this shortly. And then we're also going to talk about the entropy rate, where we now have to make mention stochastic processes. Okay. And the likes. Okay. And then we now also consider why we have to talk in terms of approximation. And all of this will lead us to the concept we have, you know, been working towards, which is data compression. I think these are the concepts we are going to be considering today. Okay. And in considering these concepts, I would love us to be a little interactive, because I want to assume we already have the notes. So I want to open the floor. What do we understand by asymptotic equipartition property? What do we understand by this concept? Any idea or any thought from us? Now, what we're actually saying is that almost everything is almost equally probable. Now, I made mention of two major concepts, asymptotic equipartition property and entropy rate. And I made mention of two interesting things. While asymptotic equipartition property applies to sequences of independent and identically distributed random variables, now the entropy rate does the same thing when we have to deal with dependent variables, okay, where we are able to pull the Markov chain, okay? But what is this all about? We are trying to say when we have a large sequence, okay, we have S1, S2, S3, all the way to a large Sn. How do we estimate the entropy, the average value of this? Then what we now want to figure out is this. Does this sequence form a Markov chain? Now, if it forms a Markov chain, then it means there is some level of dependence, right? That's if it forms Markov chain. There's some level of dependence. So then we won't be able to treat this sequence if it were independent and identically distributed. As we put as short from IID, right? So it's either these variables are independent or they are dependent. So if they are dependent, then it means that S1 forms a Markov chain with S2 all the way to Sn. And then there is an impact, okay? So that at S2, we begin to check the conditional probability of S2 given that X1 has occurred. Then at S3, we are going to be checking the conditional probability that of S3 given that S2 has occurred because of the level of dependence. Till we get to Sn, then we'll now check that Sn given that Sn minus 1 has occurred. Okay, so this is for a Markov chain because the outcome of the present variable depends on past occurrences. But if they are independent, then it means that they actually can act alone in isolation, okay? And then we cannot treat them as Markov chain because they are independent and identically distributed. So if they are independent and identically distributed, how do we evaluate the entropy of these variables? And if they are dependent, how do we evaluate their entropy? Okay, we now say, well, if we want to evaluate the entropy of the independent and identically distributed random variables, then what comes to mind is AEP, asymptotic equipartition property. But should we consider dependent variables, then entropy rate is what comes to mind because we are going to see that the entropy value grows as the variables, show their level of dependence. And if we say that for independent and identically distributed random variables, that asymptotic equipartition property comes to mind where almost everything is almost equally probable, then this brings us to the law of large numbers. Now, you must have heard of that in statistics, okay? Now, let's move on. So see on AEP. So we now say that for a sufficiently large sequence of random variables, the probability of observing a specific sequence is approximately equal to 2 to the power of minus n h of x. Now, where h of s is the entropy of the source, and n is the length of the sequence. Now, what I just mentioned here should not look strange at all. If you had looked up the likes of what Jensen and Fano's inequality means. Okay, so now we'll be reviewing all of those Fano and Jensen's inequality. Okay, so for now, there's nothing to worry about because we're going to mention everything, okay, as it were. So what we are trying to say here is that we are literally dealing with a large sequence, random variables. We want to process our data, but it's massive. That's why we want to talk about compression, right? Now, we want to ensure that the rate at which we are transmitting is less than the capacity of the channel. And the capacity of the channel is limiting, okay? Because we do not have infinitely large bandwidth to play with. So the bandwidth allocation is so narrow, and then we have to play with some kind of narrowband technology. So we have to figure out a way to maximize the bandwidth. And that calls for source data compression. And what we are trying to say is that when the sequence is sufficiently large, the probability of observing a specific sequence is approximately the same as this. Okay? This is what it is. And this is what Fano inequality says. So what did Fano say? Now, according to Fano's inequality, it says that the probability of, say, two identically independent and identically distributed random variables with entropy H with probability distribution, say, we're dealing with 2 when x is the same as x prime, for instance. These are the two probability distributions. So we are literally considering the probability distribution of 2 independent and identically distributed random variables. We're not trying to say that this probability is given as to be the same, or let's write that is greater than or equal to 2 to the power of minus h of x. Okay? Now, this is what we have. But now, we don't just have 2. We now have x1, s2, s3, all the way to Sn. So if we now have to observe the probability distribution of a large sequence assigned with this probability distribution, then we can as well tell that the probability based on what we just mentioned is going to be as close as, based on Fano's inequality, we now have n of this operation, okay? Here we have 2, okay? Just one length in between. But now we now have up to n length in between. So this will approximate something like 2 to the power of minus n H. Okay? Does this make sense?
Please, sir, come again.
Now, we can, now from what Fano said, okay? Now, Fano said, when we have two independent and identically distributed random variables with entropy H, and then with a probability distribution such that they have equal probability distribution. So it means that they are identically distributed, right? You get the point. They're identically distributed. So if that is true, that their distribution is the same, meaning they have same probability distribution. That's why they're identically distributed. But this time, they are independent. That their probability distribution is greater than or equal to 2 to the power of minus h of x, where h of x is the entropy, the source entropy. So we are now looking at a large sequence beyond two independent and identically distributed random variables. So if we now have more than two, so such that these random variables now forms a very large sequence. Don't forget when we talked, we are still talking about asymptotic equipartition property, and we said, well, here the law of large numbers comes into play. Law of large numbers, because we are dealing with large sequence. And now this is the large sequence. So we are not just dealing with two random variables. We are dealing with n random variables, and they are identically distributed. Okay? So it means that if I should consider x1 to s2, so they do not form a Markov chain, so we cannot connect them together. I consider s2. So here we have 2 minus h of x, for which here we are considering at n equal to what? Is it 2 or 1? So we are moving from this point to this point. Now, literally, I'm just one random variable away, right? So at this point, n is the same as 1. Now, what if I move to my third random variable? So I'm two random variables away. So this now will reduce to 2 to the power of n, 2 h of x, right? Now, by the time I go extremely large numbers, then what I'm going to be having approximately will not be this anymore. So it means that this probability distribution is going to grow by n at n rates.
Sorry, taking you back with this flow, definitely the n should be n minus 1. Since it is going to be reducing.
No, not n minus 1 yet.
We're going to infinity.
No, I'm talking about the 2 raised to power n.
No, it's not going to be, it's not going to be n minus 1 yet. It won't be n minus 1. I understand your reasoning. Okay. Now I'm going to quote Jensen's. What did Jensen say? Now, according to Jensen, it says that if we have a random variable with probability distribution P of x, okay? Now, according to Jensen's inequality, it says that if, for instance, f forms a convex function, okay? Because we always want to target convexity in terms of optimization for ease of convergence, then the expected value of f of x is greater than or equal to f of the expected value of x. Okay? So that if we have 2 to the power of the expected value of log p of x, then this is going to be less than or equal to the expected value 2 to log p of x. Now, this technically implies 2 to the power of minus h of x will be the same as 2 to the power of the expected value p of x log p of x, which is less than equal to the expected value p of x 2 log p of x, which will now be the same as the expected value p squared of x. Now, this is what Jensen talked about, okay? In terms of the probability max function achieving the bounds with equal probability or with equality, okay? Now, this literally follows from this assumption, okay? Which is Fano's inequality. Now, at this point, we are literally dealing with equality in terms of the uniform distribution, because here we have identical distribution. So this just tells us that they are independent. Okay? And then, if we now have to take this a little further, so let's assume we now have this large probability distribution assigned to an observed sequence. What are we going to be dealing with? Okay, so let me come back. Let's take things back. Now, so I already mentioned the law of large numbers. What does the law of large numbers say? The law of large numbers talks about averaging the large sequence, okay? So if, for instance, we have large sequence, then the law of large numbers therefore describes that the average of the results obtained from the large number of trials should be close to the expected value, which is the mean, right? So technically, we are saying that we're going to take a limit for which n extends to infinity, such that I is equal to 1 to n, and here n extends to infinity, so that we have s sub I over n, which is the average value. And we're saying this is the same as the mean, and that is the expected value, okay? Then we can now say that this is the same, if we open this up, this is the same as 1 over n, the summation of s of I taking all values from 1 to n. But take note, n extends to infinity. Okay? So if n is extending to infinity, n is sufficiently large, so we cannot be dealing with the parameter as n minus 1. It's going to be n. Hello?
Yes, sir.
Now, because what we are literally dealing with is that this variable s of I is large. Now, our n have gone way beyond n minus 1 all the way to n to infinity. So it's really large. It's something that we may not be able to just, analytically measure at this stage. So when we get to that point, how do we perform data compression? That's why, well, let me not jump the gun. That's why we are going to be having what we call the typical set and atypical set. Because mind you, we are dealing with large numbers. But when we talk about the law of large numbers, despite the fact that the average value at this point tends to the expected value, we have two variants of the law of large numbers, the weak law of large numbers and the strong law of large numbers. Now, the difference is that for the weak law of large numbers, we see that the average value tends to that expected value in probability. Why for the strong law of large number, it is certain. So we have two strong law of large numbers. So here, sample average converges in probability towards the expected value. Why for the strong law of large number, the sample average converges almost surely to the expected value. Now, the difference is that this is surely, this is probable. Okay? And now our AEP is analogous to the law, the weak law of large numbers, the asymptotic equipartition properties. Okay? And what does it say? Now, asymptotic equipartition property, which is analogous to the law of the weak law of large numbers, it says that the average value 1 over P of x1, s2, all the way to Sn tends to the entropy, okay? Which is the expected value of log P of x, right? And now this is the same as negative 1 over n log P of x1, s2, up to Sn, which tends to the expected value, okay? So here, as we're talking about the expected value, is in probability, right? This would be minus, right? Over P of x, which is the entropy. And we already know that these random variables are independent and identically distributed. And this probability distribution is the probability of observing this sequence that is large, sufficiently large. Okay? Now, if this is what we've got, this is what we've got. Now, recall that we already invoked the Fanos inequality, okay? So that for two independent and identically distributed random variables, this probability distribution for x being the same as x prime is greater or equal to 2 to the power of minus h. Yeah? So what is now going to happen if we are now dealing with large random variables for which n tends to infinity? What will be the probability? So now we are talking about the probability of S1, S2, all the way to Sn. This will be approximately what value?
2 raised to power minus n into brackets
2 raised to power minus n h.
h.
Good. Now, what if all the events are almost equally surprising? Then we are going to be adding the error value to this, right? Now, this is what we now have. Now we now have that the probability distribution of this distribution is approximately the same as 2 to the power of minus nh. Now, if all of these events, these random variables, are equally surprising, then what will happen? What will happen? So it means that the probability distribution of this outcome is going to be the same as 2 to the power of minus n, h plus or minus the error. And this must be approximately equal to 1. It can be greater than 1, right? So that if we now talk in terms of convergence and probability, given a sequence of random variables that is sufficiently large, S1, S2 all the way, we can now conclude that the sequence of random variables x1 all the way to Sn converges to a random variable x. When these conditions are met, say in probability, if for every error value greater than 0, the probability of mod Sn minus x is greater than the error value, right? This tends to 0. Okay? And also, in mean square, if the expected value of the mean squared error, tends to 0. And then we are going to be having this, having the probability of 1 when we say the event is almost surely if the probability, should we take limits as n tends to infinity, for Sn being the same as x, will be equal to 1. So it means it is almost surely. So technically, the asymptotic equipartition property theorem states that for sufficiently large random variables that are independent and identically distributed, the average value of this distribution tends to the entropy in probability. This is an approximation, okay? And one challenge is that, is this approximation foolproof? Now, this is what I'm saying. The asymptotic equipartition property now states that for x1, s2, s3 all the way that are independent and identically distributed, having the probability distribution P of x is such that the average value in probability x1, s2 all the way tends to the entropy in probability. And recall that it is the weak law of large numbers that also tend to the average value in probability. This we know is the average value, entropy. Okay? Is this clear for now? Because this technically is more like saying this is the average value log P of S sub I, where I takes on all of those values. And we already know that this is more like the expected value, this average value. So this will give us negative expected value log P of X. And we know, and this is in probability. And this we know is the entropy, H of X. So we are literally dealing with the source entropy. Okay? Now that we have, related with this, don't forget I mentioned earlier that for sufficiently large sequence of random variables, that the probability of observing a specific sequence is approximately 2 to the power of minus nh of x. Okay? Now, what I want you to take note of is that for most long sequences, x1, s2, s3, all the way to say Sn, forms a typical set. And all of them occur, or better say, have the same probability of occurrence. That is why they are identically distributed. Okay? Now, if for instance, now where I'm going to, you need to take note, I have evoked the property typical set. Now, it's a typical set largely because they are identically distributed. So for large random variables having the same probability of occurrence, we can say they form a typical set, right? Isn't it? Hello? Am I alone?
Yes, sir. Yes, sir. We can hear you, sir.
Okay. Now, if you are with me, so let's say we have x1, s2, s3, all the way to Sn that are independent and identically distributed random variables. And these random variables have the probability mass function P of X. Now, we now say for very large N, say for large N, the joint probability distribution can be expressed as P of x1 being the same as x1, s2 being the same as s2, all the way to Sn being the same as Sn, is approximately the same as 2 to the power of minus nh of x, which we already described. And here, h of x is the same as sigma, x being an element of x, p of x, log base 2, this is negative, being the entropy. Of the random variable x. So what we are trying to say is that the asymptotic equipartition property, AEP, implies that the set of possible sequences can be divided into two groups, so that we have the typical set for which the sequences occur with high probability, and their total probability is close to 1, but not necessarily 1, and the atypical set for which their probability of occurrence is very low, okay? Now, if this distribution, that is AEP, now implies that we have this sequence divided into two groups, okay? One typical set in which the sequence or sequences occur with high probability, and their total probability is close to unity, right? It's close to 1. And then we have the atypical set in which they occur with very low probability. So what we are now going to be concerned about in terms of data compression will not be the atypical set. So we want to consider the sequences that occur with high probability, which forms the typical set. And once we're able to map those, then we should be able to get a typical representation of that data in terms of the average description. Is that okay?
Yes, sir.
So technically, the asymptotic equipartition property therefore allows us to approximate the source. That's why I call this a topic of discussion, approximation of entropy. Okay, so it literally, okay, let's write that down in case you want to document it. So the asymptotic equipartition property allows us to approximate the source by compressing its output efficiently using the entropy as a lower bound. And when we get to channel coding, you see that with this, we are also able to determine the capacity of the communication channel, okay? Now, okay. So we just brought in another interesting activity, the, what's it called now? Typical set. Now, since the typical set occurs with high probability, we can now say that the typical set is where the sample entropy is close to the true entropy. And the atypical set is one that contains other sequences. So this contains other sequences. So any property that is proved for the typical sequence will then be true with high probability. That's the idea. And with that, we are good. So if we now want to make a formal statement for the typical set, which is usually described as A sub E super N, with respect to the probability distribution, having that probability distribution, we now say that this is a set of sequence, say x1, s2, all the way to Sn, being an element of S super N with the property 2 to the power of minus N, h of x plus the error value, less or equal to the probability distribution, S1, S2, all the way to Sn is less or equal to 2 to the power of minus N, h of x minus the error value. Okay. And this, we can now say that the typical set has probability nearly 1. And all the elements of the typical set are nearly equiprobable. Okay? They are identically distributed. And then the number of elements in the typical set is nearly 2 to the nh. Okay? So the typical set is therefore a small set that contains most of the probability. Now, if that is so, now there's one thing you should bear in mind, which is that the entropy itself is the average number of bits needed to represent a random variable. And that is what we need for data compression. And it is dependent on the probabilities of the random variables, isn't it? Because when we define the entropy, we say the entropy, which is the expected value, log negative P of X. So the entropy itself is dependent on the probabilities. And we're now saying that the typical set contains most of the probabilities. So since the typical set is a small set that contains most of the probabilities, to evaluate the shortest description for the sequence of the random variable, we could divide this sequence into a typical set and an atypical set, which is the complement of the typical set, and afterwards run our evaluation. I don't know if this is clear. Hello? Hello? Can you all hear me?
Yes, Doc, we can hear you, sir.
So technically,
yes, sir. Last one, sir.
Okay, now I said the entropy is a function of the probabilities. And now the typical set contains most of the probabilities, right? So in other words, if we are able to evaluate the entropy of these typical sets, we should be able to come up with the shortest description length to describe that sequence. That is where data compression comes from now, right? We already said that the typical set contains most of the probability. And now the atypical set is the complement of the typical set, right? This is atypical. This does not contain most of the probabilities. The atypical set does not contain most of the probabilities. So in other words, the sequence, say we have a very large sequence. Now this sequence, from what we said, can be divided into two parts: typical and atypical. This is A to the N. Why this is the complement, right? So we are saying this typical set contains most of the probabilities. And if this contains most of the probabilities, so it means that if we are able to take the average of this, that gives us the entropy. And that value, with that value, we are able to investigate, or better say, evaluate the shortest description length of the sequence. And if we're able to evaluate the shortest description length of the sequence based on the typical set, that gives us the compression we need. That's what I said earlier. Does that make sense?
Yes, sir.
Okay. So if that's what it is, then we can now we can therefore develop a code going by these activities. And then we now begin to talk about the length of the code, okay? And the length of the code, which we call the expected length, is the same as the expected value of the length, L of X to the N. Well, we are going to relate with this shortly when we talk about data compression. So just take things cool. We'll move through this step by step, okay? So now that we have now mentioned that for us to be able to now generate a code, all we need to do is the shortest description length. Now, this shortest description length is a little tricky because now we are talking about length. How about entropy? Did we just stop talking about entropy? Because we want to figure out the shortest description length. Now, we talked about the average length, which is entropy. And we're not talking about the shortest description length. Now, in describing the shortest description length, we are saying, well, we have been able to figure out the typical set of this sequence that contains most of the probabilities. And we know that the entropy is a function of the probabilities. And once we are able to take that average value, we are good. We are able to figure out the shortest description length. And now for us to be able to design a practical code or a code in practice, we are more concerned about the expected length of that code. And now we know if we are able to tell the length, then this is the expected value of this length. Okay? Now, recall that we have this sequence S of n. And this sequence is divided into two blocks, the typical set and the atypical set, which is the complement. So the expected length in this case of this sequence will now be the sum of the expected length of the typical set and atypical set, isn't it? Where this is Sn is an element of the typical set plus the expected length P of Sn, L, Sn, for which in this case Sn is an element of the atypical set complement. And if we now consider prefixing, okay, that's the total length, and I think I skipped that, okay? So by the time we talk about the prefixing and all of that, then we'll be able to reduce this in terms of analysis. But I just want us to take this first, okay? So this is what we now have. Now, if we now take things up from here, then we now have to figure out the expected length of this random variable. Because in essence, we are literally interested in the typical set. Now, if we are interested in the typical set, it means that the atypical set is a form of error for us because it does not contain most of the probabilities. Is that okay? Hello?
Yes, sir.
Okay. And then with that, we should be able to conclude our mapping such that the expected length will now be a function of the typical set, for which we are able to estimate the entropy already, right? Recall, this contains most of the probabilities. Now, this is more like a fair description of a sequence that is independent and identically distributed. But what if we have a sequence that is dependent? We now have a sequence. Now we want to talk about a sequence that is dependent. So that is what brings us to entropy rate. And we say that the entropy rate is equally the average amount of information. Is the entropy is the average amount of information produced per random variable in a stochastic process. Now, you should underline this word per because there is some level of dependence here. Okay? So it's more like generalizes the concept of entropy for stationary and ergodic processes, but we'll come there. So the idea now is that for a stationary stochastic process, say S1, S2 all the way, now the entropy rate H of X is given as taking limits for which n tends to infinity, 1 over n, H of X1, S2 all the way. Where this is the joint entropy. Of the n random variables. So what we now want to talk about is, what if S1, S2 are independent and identically distributed? So what will happen to the entropy rates if they are independent and identically distributed? So it means S1, S2, S3, S4, S to Xn have the same distribution. What would be the entropy rate in this case? I need your feedback, please. So we have given that the entropy rate gives us this growth for which n tends to infinity, 1 over n. Now, this is not in logarithm or in probability, but S2 all the way. So we know that this is, from what we said, this is joint entropy. So the question now is this: if these random variables are independent and identically distributed, what will be the entropy? What would be the entropy? Hello? Can someone help out? Are we still in class?
Yes.
Okay. Now, like we said earlier, if they are, independent and identically distributed, then the entropy rate will simply be the entropy of a single variable. So it means that H of X will be the same as H of X1. Now, how about if they are dependent? Because if they are dependent, then it means that it will form a Markov chain, isn't it? So if S1, no, let's use X, Y, Z for instance. If X forms a Markov chain with Y, forms a Markov chain with Z. So at this point, we are going to be talking about the conditional probability, say P of Y, given that X has occurred. While at this point, we are going to be considering the conditional probability of P of Z, given that Y has occurred, right? So the entropy rate will now account for the dependencies between variables. I don't know if you get what I mean. Here we have P of X. So in this Markov chain distribution, we are now going to begin to talk in terms of conditional probabilities because there is some level of dependence. Hello? Hello? Are we
Yes, sir. We are with you, sir.
Now for the scenario where they are independent and identically distributed, all of these conditional properties are equal to 0. So that the entropy will now be the entropy of a single variable. But when they are dependent, they are not equal to 0. Okay, because X and Z are conditionally, dependent here, So technically, Y can learn or observe X, while Z can observe X from Y. Okay? So this now brings us to the growth in entropy. Okay? So that's why the entropy rate is typically referred to as growth in entropy. And if we take a typical example, let's say a typewriter, for M equally likely outcome. So it means that we have M to the N. This is for a typewriter, for instance. Then it means that H of X1, S2, all the way to Sn will be the same as log Mn, right? Isn't it? 1 over n, right? Which is the average value. That's that. So this will now be n over n log m, which will now be log m. So in this case, we now see that the entropy rate is seen to be the best achievable data compression. Okay? Okay. Now, we already played with Markov chain and all of that. So I think I will leave that for your study, where we talk about stationary Markov chains, stochastic processes. I think we have all of those, time invariant and all of those stuff in the previously updated notes. So I'll just jump right into some other important details that I would love to address here. So what other information do I want to pass across? Okay. So just from this simple analogy, we can see that the entropy rate helps to determine the minimum average number of bits needed to represent a stochastic process, okay? And it also provides insights into what's it called now, the randomness or predictability of the process, okay? So far, we can see that in comparing these two cases, two approximation techniques, the AEP and the entropy rate, and we said, well, this is when we talk about independent and identically distributed random variables, and now when we have to deal with dependent random variables, and here they form Markov chain, and we see that the entropy rate grows, right? The growth in entropy. So we now begin to talk about growth in entropy, okay? But so we now see that the asymptotic equipartition property justifies the use of the entropy rate as a measure of the typical behavior of a stochastic process, okay? So here we see that it shows that the probability of observing a typical sequence is dominated by the sequence with probability that is as close as possible to 2 to the power of minus n h of x. And we know h of x is the entropy of the process, okay? Now, one other thing I would love us to now consider in dealing with all of these is that all of these concepts are very, very useful in source coding. And that brings us to data compression. Okay? So when we now begin to talk about source coding, for instance, when we talk about source coding, for instance, we see that the asymptotic equipartition property justifies the Shannon coding theorem. And what does it say? It states that the source can be compressed to the entropy of the source bits per symbol without losing information, for which we saw the typical set. And it also ensures that compression schemes, like we are going to see shortly, Hofmann's coding and arithmetic coding are efficient, okay? And if we are able to perform source coding, we also see that the asymptotic equipartition property in the context of channel coding helps identify reliable transmission rate, okay? Because it literally analyzes the typical sequence, okay? So if we are able to analyze the typical sequence, then we know the sequence with the most or highest with the most probabilities, and then we are able to enforce reliable transmission also. And we can also use that in channel coding to ensure error-free communication, where we were trying to take things in phases. So once we are done with data compression, then we'll go to channel coding. Okay. And then we've mentioned some key points about the entropy rate. And if this is for our asymptotic equipartition property, we also see that the entropy rate literally provides the theoretical limit. The theoretical limit for lossless compression. Of a stochastic process. Okay, so technically the compression algorithms literally aims at approaching the entropy rate. Okay, and then we see that the entropy rate helps in quantifying the uncertainty in sources, and this also helps in analyzing the capacity of communication channels. Okay, and then we can literally investigate the applications, okay, in describing a whole lot. But the bottom line is this helps us in figuring out a reasonable approximation for a large sequence. Okay, and once we are able to do that, boom, then we arrive at what we call data compression. Okay, before we move on, any question, please? Any question? Any question, please? Hello? Mr. Wale Ojo, any question? Is Mr. Wale Ojo with us?
Yes, I'm with you, sir. No question yet, sir.
Okay. Okay, so I think we've been able to build sufficient background to now move into data compression. We started with the information measure. We talked about the data processing algorithms, and then now we've been able to talk about techniques for approximating sufficiently large sequence. Because if we have to talk about compression, then it means the sequence must be sufficiently large, where the random variables extend to, say, infinity, okay? And now we don't have infinite bandwidth to transmit this source sequence. So we are left with no other option than to find an approximation to the bit sequence that can be used for transmission. And then we've considered two different scenarios whereby the random variables are independent and identically distributed, and then the asymptotic equipartition property, which is analogous to the weak law of large numbers, helps us to approximate the average value in probability. And once we are able to find the approximate value in probability, then that is typical of the entropy. And then we're also able to say that, well, this large sequence from deductions made, that it could be grouped into two major sets, the typical set and the atypical set. And that once we are able to figure out the typical set, then we know that the typical set contains most of the probabilities, and the entropy is a function of the probabilities. And that should be sufficient in describing the compression of this large sequence without losing any information. Okay, and then we also made mention of the entropy rate, that should these random variables be dependent, whereby they form Markov chain. Based on the principle of Markovity, we now realize that, well, there's some level of dependence with these random variables. And then this entropy rate, we see that it grows, okay, for stochastic processes. And then we were also able to figure out the approximation to estimating the entropy, which forms the basis for the compression. Okay, now that we already know that the entropy is literally the data compression limit for us, in that it tells us the number of bits needed in the random number generation to generate the code that will be transmitted through the channel, then we can now say that data compression is achieved by assigning short description to the most frequent outcome of the data source. Okay? And for us to do that, if we have certain random variables occurring frequently, then we want to give them short length. And then for those that occur, that are not that do not occur frequently, that are less frequent, we assign longer length. So by so doing, we are able to come up with a compressed data. Okay, so we now say that a source, or a source code C, for instance, for a random variable X, is a mapping from, say, X the range of X to D steric, the set of finite length strings. Of symbols from a D array alphabet. And in this case, if we say that C of X is the code word corresponding to, say, S sub I, and then L of X is the length of the code word, then the expected length, say L of C, of a source code C of X for the random variable X with probability mass function P of X, can be described as the expected value of the length of the code word, where S is an element in X. Okay, so now if we have been able to show that for us to be able to achieve data compression, we have most frequent and less frequent outcomes. So here we assign short length, and here we assign long length. So that's how we're able to achieve compression. So we're going to see how this works. So what we are now saying is that the expected length that we are supposed to get after compression is the expected value of the length of the code word. Okay? And then by the time we compare this with the entropy, it should be such that h of s should be less than or equal to this expected length for us to be able to check for optimality of the code. Okay? Now, if the entropy is not as close as possible to this length, then we are not going to get optimal codes, because the efficiency of the code is the same as the ratio between the entropy and the expected length of the code. And then the redundancy will be the same as 1 minus this. And from this, we can see that the efficiency of the code reduces as the redundancy increases. So the less the redundant bits, the better the compression. And that is why we say that we achieve compression by removing redundant bits, and then we achieve error control or reliability, transmission reliability, by adding redundant bits. Does that make sense? Does this make sense before I move on? Hello?
Yes, sir. It makes sense, sir.
Yes,
But
sir. Yes, sir.
is it not counterintuitive, given that we want to have as much compression as possible so that we are able to, recreate the information?
Okay, what's counterintuitive now? Adding redundant bits and removing redundant bits, right?
Yes, sir.
Absolutely, yeah. Now, we'll talk about that quickly. So we talk about removing redundant bits and adding redundant bits. So this is your communication system. We have source coding. Then we have channel coding. Then we have the channel, for which we have noise. Then we have channel decoding. Then we have source decoding, right? Now, before we move into the channel, we have to do compression. So we remove redundant bits. We remove redundancy, right? So as to transmit over the channel. Now, for us to be able to build immunity against the channel noise, we add redundancy. But in controlled measure. Is that okay? So this forms the entire communication process. So we are not adding redundancy in such a manner that we overflow the channel buffer. Is that clear, please?
Yes, sir.
So by adding this is what we call error control coding, which we are still coming to. Okay, we'll see how we do this. Error control coding. So we are going to talk about those techniques for doing this. Okay. That's where you talk about all of those, your Hamming codes, Rich Solomon, cyclic codes, block coding, convolutional coding, turbo codes, okay? They are strictly meant for error control over the channel. So there you're adding redundancy in control measure. But for us to be able to transmit over the channel, looking at our analog that we've converted to digital, we've digitized, and now we have some bit sequence. So how do we map this to certain symbols and all of that? Is that not going to overflow the channel? Then we want to use the average description length to describe those bits without losing information. Then that is source coding. So while we are doing that, we are literally removing bits that are not important. Okay? So we are mapping it in such a way that we don't lose information, but we're able to use the minimum number of bits to represent what is being transmitted. Is that okay?
Yes, sir.
Okay. So now that we've talked about this, so let us talk about a few codes, okay? So we have some codes so that we know what kind of code can we use for for compression. Can we just use any code or any sequence? Okay, so if we do that, are we not going to confuse things? What if A is seen as 001 and B is also seen as 001? How are we going to tell the difference? So is this possible in source coding? Or is there a rule to say, well, if we assign 001 to A, then we can't assign 001 to B? Okay, or if we assign 00 to A, can we assign 001 to B? Okay, is there any rule that says this when we are compressing? Because here we see that 00 is a prefix of 001, right? So is this not going to confuse this to A1 rather than saying it is B? So how do we really tell the code mapping? Okay, so we have some codes, okay, of interest. And the first we are going to be talking about is non-singular codes. So when we talk about non-singular code, this is literally a code in which no two distinct symbols are encoded to the same code word. Okay? So it means that in this case, each symbol has a unique representation in the encoded form, ensuring that the decoding process is unambiguous. We don't want to confuse things when we are decoding. So for non-singular codes, they are essential for reliable communication since they prevent errors and loss of information during transmission or storage. So at this point, the code is said to be non-singular if every element of a range of X maps into a different string in D, okay? So it means that S, for instance, is mapping to a different string in D, such that X is not the same as the inversion of S. Therefore, the code word C of S is not the same as the code word C of X inverse, because here we are doing one-to-one mapping. And this is literally sufficient for unambiguous decoding. Unambiguous decoding. Okay? Because here you see that X inverse is for decoding. So if we are transmitting X, for us to recover X, we have to take the inverse of that in the decoding process. So if we are encoding, so decoding, this is not equal to this, because decoding, we see the inverse of this. Okay, because this, we call this inverse mapping. Okay, does this make sense? So it means that we cannot map S to X in D. We could map S to Y in D, okay? Does this make sense? Hello?
Yes, sir.
Okay. So the next point here is extension codes. Now, when we talk about extension codes, it's literally the process of designing a larger code from a given code, okay? And we could do this in so many ways. There are so many techniques for this, okay? So it means that if, for instance, C asterisk is the extension of a code C, for instance, now, when we talk about the mapping, we are literally saying that C of X1, S2, all the way to Sn will be the concatenation of all of these codes. Okay, so let's assume this is 0, 1, and this is 1, 0. Now the extension code is going to be C of X1, C of S2, which will be the same as 0, 1, 1, 0. Okay, but now when we talk about extension codes, this is just one way of achieving extension codes, which is concatenation. We can also achieve extension codes by repetition. So it involves repeating each symbol or bits of the original code multiple times, okay? So I say 0, 1, 0, 1, 0, 1, 0, 1. So this is more like an extension code, okay? Now, this is by concatenation. We are bringing, you know, we are concatenating the original codes, bringing 2 or more of those codes together. Now, we can also achieve extension codes by adding parity. Okay, so there we are literally adding more bits to the original bits. Then we can also do this by, so we have talked about how many, by concatenation, by repetition, by adding parity. Then we can also do that by increasing the symbol size. Okay, so we can increase the symbol size, increasing the symbol size. So it involves increasing the number of bits per symbol in the original code. Okay, so there, let's say you want to convert a binary code to a ternary or a quaternary code. Okay, so you are literally extending the code. Okay, now another interesting code is uniquely decodable code. So it means that not all codes are uniquely decodable. Okay, so when we are compressing, so we'll have to ensure that the codes are uniquely decodable. Okay, so I would say that a code is uniquely decodable if its extension is not singular. What that means is that any encoded string is in a uniquely decodable code has only one possible source string producing it. Okay, so there we now say that this code literally possesses the property that ensures that a sequence of encoded symbols can be uniquely decodable without any ambiguity. Okay, so for the uniquely decodable codes, they ensure that no code word is a prefix of another code word. Okay, so this literally prevents ambiguous decoding. Okay, so technically it allows for unambiguous decoding. So it means that if A is 1, 1, B cannot be 1, 1, 0, because 1, 1 is a prefix of this code. It means A is a prefix of this code. So technically, this code in this coding scheme is not uniquely decodable. This is not uniquely decodable. So it means that when mapping bit sequence to symbols, we must ensure that each symbol have a distinct code representation for them to be uniquely decodable. Does that make sense, please? Hello?
And recap that for me.
Okay. So now let's assume I want to transmit AB from my source. This is my source. This is my destination. So I want to transmit AB. So this is supposed to come here. So this is going to see 1, 1, 1, 1, 0, right? So when we get here, how are we going to know what this is? So this may just tell me, now this is A, B, right? So this is going to tell me AA 0. Now it could also say, yeah, this is what it's going to tell me. Whereas this is supposed to be AB. Do you know why? Because A is a prefix of B. So hence, it is not uniquely decodable. So if we want to actually ensure a uniquely decodable code scheme here, probably A is 0, 0, then probably B is 1, 1. So once we transmit AB, I'm going to see 0, 0, 1, 1. So I know this is A, this is B, because no code is a prefix of the other. So it means it is uniquely decodable. Does that make sense?
Yes, sir. It makes sense now.
It does, sir.
Okay. So the next thing we'll talk about is instantaneous codes. So when we talk about instantaneous codes, we say, well, this is actually a uniquely decodable code where no code word is a prefix of any other code word. And no code word is also a proper suffix of another code word. So what we're trying to say is that each code word uniquely identifies a message symbol without the need to look ahead or backtrack during decoding. So it means it is instantaneous. It is an instantaneous code. I don't know if you got that. So because what we're trying to say is that each symbol can be decoded as soon as the corresponding code word is complete. It is not necessary to see bits of some other symbols before we want to begin to decode it, okay? And we can now say that a uniquely decodable code is said to be instantaneous if it is possible to decode each code word in a sequence without referencing to any other code word. So I think the uniquely decodable and instantaneous codes seem to be tricky. Hello? Hello? Are we on the same page?
Oh, yes, sir. Yes, sir. We're still here, sir.
Okay. So can we move on?
Most definitely, sir.
Okay. So if we have been able to pick some of these details where we have been able to talk about singularity, we've been able to talk about non-singular codes, we have been able to talk about extension codes, we've been able to talk about uniquely decodable codes, we've been able to talk about instantaneous codes, then what is the condition to check that a code is uniquely decodable? Now, the sufficient condition to check for a code's uniquely decodability is what we refer to as the Kraft inequality. Okay, so the Kraft inequality actually tells us that any instantaneous code or prefix code over an alphabet of size D and code word length, say L1, L2, all the way to Ln, which we could describe as L sub I, must satisfy the inequality sigma I D to the power of L sub I less or equal to 1. This is the Kraft inequality. So if we are given a set of code word length that satisfies this inequality, then what we are trying to say is that there exists an instantaneous code with this code word length. But if they do not satisfy this Kraft inequality, then there's a problem with decodability. So if we are given an infinite prefix code, now such that I now ranges from 1 to infinity, then this is more like an extension to the Kraft inequality. So we now have d to the power of minus li less or equal to 1, and then we call this the extended Kraft inequality. So we're not saying that the code is sufficiently large as it extends to infinity. So it also states that for any countable infinite set of code words that form a prefix code, then the code word length must satisfy the extended Kraft inequality. And we can also say conversely that if we are given the length, the code word length, L sub I, satisfying the extended Kraft inequality, we can literally construct a prefix code with these code word lengths. And then, in general, the Kraft-Macmillan now position this to say that the code word length of any uniquely decodable DRA code must satisfy the Kraft inequality, regardless of the length, whether it extends to infinity or not. So if we are given a set of code word lengths that satisfies this inequality, it is possible to construct a uniquely decodable code. So with this, we can literally construct a uniquely decodable code. So I think we can look up a simple example, okay? Okay, so I think we have some consequences here, okay? What happens if there's equality, okay? And what happens if there is inequality? And what happens if this does not hold? Let's assume the Kraft inequality is greater than 1. So if it's greater than 1, obviously, the code is not uniquely decodable, okay? Now, if it holds with strict inequality, then the code has some redundancy. So it means that it's less than 1. But what if strict equality holds? So it means that the code is a complete code. But the fact that it is a complete code does not mean it is uniquely decodable, okay? So the implications, so let's say implications of this inequality is that if strict equality holds, so we say that the code is a complete code, okay? The code is a complete code. But that does not mean it is actually uniquely decodable. We still have to do some other things, but it means that we can actually construct a uniquely decodable code, okay, if that is true, okay? Now, if strict inequality holds, it means it is less than 1. So it means the code contains some redundancy, right? So the code has some redundancy. And if it does not hold, so let's assume this inequality does not hold, say it's greater, okay? So let's assume this inequality does not hold. Say it's greater. Then we cannot construct a uniquely decodable code, okay? So there we can say the code is not uniquely decodable. Okay? Is this clear? For now, is this clear, please?
Yes, sir.
Okay. Now, we also have the optimal code. We say a code is optimal if it is instantaneous and has a minimum average length for a given source and given the probability, okay? So we'll now check for optimality of some code. So let's look at a simple example. So let's assume we have the symbols, then we have code A, code B, then we have code C, and then we have code D. So let us use this. So I have first code, I have the second code, let's say I have the third code, and let's say I have the fourth code. So we have this, we have this, we have this, and we have this. Okay. So let's assume we have S1, S2, S3, S4. These are the code words. So for our first code, we have 00, 01, 10, 11. Then for the second code, we have 0, 10, 11, 110. Then code C, we have 0, 11 for symbol S2, and 100 for symbol S3, and 110 for symbol S4. Then for code D, we have 0, then we have 100, we have 110, and then we have 111 for code S4. So now we want to consider these codes to check which of these codes are prefix free and which of them are uniquely decodable. Now, for us to be able to assume code for data compression that, and then we've decided to say, well, this code, this sequence can be transmitted over this channel, we have to ensure that they are prefix free and that they are uniquely decodable. We don't want to get things messed up at the receiving end, okay, at the point of decoding. So we want to consider the first code. Now, for the first code, we can look this up by inspection. Code S1, code S2, code S3, code S4. Well, I don't think any code is a prefix of any code here, right? Because this is 00, this is 01, this is 10, this is 11. So they seem that now there's no code is a prefix of another code also, right? So let us apply the Craft inequality to code A. So we know from Craft inequality, I in this case is 1 to 4, 1, 2, 3, 4. And then D is 2. Okay, that's the size of the code, is binary, so it's 2. And then we have negative L sub I, where L sub I is the length. So in this case, what is the length of each code? X1, the length is 2. We have 1, 2, 1, 2, 1, 2, 1, 2. They are all 2, right? So in this case, we are going to be having 2 to the power of minus 2 plus 2 to the power of minus 2 plus 2 to the power of minus 2 plus 2 to the power of minus 2, which is the same thing as 1 over 2 over 2 plus 1 over 2 over 2 plus 1 over 2 over 2 plus 1 over 2 over 2. Okay? So that's literally 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4, which is equal to 1. Okay? So here, this code is complete because strict equality holds is equal to 1. And by inspection, we can see that it is prefix free, right? No code is a prefix of another, and it is uniquely decodable. So we can use these codes to represent each of these source symbols. Is this clear?
Yes.
Now, let us consider code B. So the same way we have I taking from 1 to 4, we are dealing with binary, so that's the size, 2, negative Li. So in this case, we have for x1, that is 1 over 2 to the power of 1, right? Plus the second here, we have 2, the length is 2, that's 1 over 2 to the power of 2, plus 1 over 2 to the power of 2, and the length here is 3, we have 1 to 3. So 1 over 2 to the power of 3. So that's 1 over 2 plus 1 over 4 plus 1 over 4 plus 1 over 8. So this is going to give us what? 1, this is half plus half, 1 over 8. And this is greater than 1. So by the implication of the Kraft-Macmillan inequality, it means that the Kraft inequality is not satisfied. And as such, this code is not uniquely decodable. It is not uniquely decodable. Now we know based on these strict equality holds, the code is complete. It's a complete code. It is prefix-free. And it is also uniquely decodable. So should we use this to represent our source symbols? Then we're going to run into serious issues. 0 is a suffix of S2. It is also a suffix of S4, right? 1 is a prefix of S4. 10 is a suffix of S4. So it means this code does not qualify. And as such, it is not uniquely decodable. So we don't want to use something like this, else we are going to run into some issues. Okay? So this is a no-no. Does that make sense? When constructing your codes? Hello? Are we still together?
Yes.
It makes sense, sir.
Okay, so now we now go to code C, for which we have I taken from 1 to 4, 2 to the power of minus s of I. And here we have 1 over 2 to the 1 is one code, plus 1 over 2 to the 2, plus 1 over 2 to the power of 3, plus 1 over 2 to the power of 3. So this is 1 over 2 plus 1 over 4, plus 1 over 8, plus 1 over 8. And this is going to give us what? This is 1 over 4 plus 1 over 4. So once again, this is equal to 1, right? 1 over 4 plus 1 over 4 is half plus half that. Now let us look up this code. We now see that this code literally satisfies the inequality, the Kraft inequality, but it is not an instantaneous code. It is also not prefix-free because 1 is a prefix of S4. So it means that although it satisfies the Kraft inequality, it is not uniquely decodable. So we want to avoid this kind of code too, right? Does that make sense?
It's because it's not prefix-free, right?
Yeah, it's not prefix-free. So it means it's not an instantaneous code, because for us to have instantaneous code, it means that a code should not be a prefix of another so that it will be uniquely decodable. So in this case, this is not uniquely decodable. It is not a uniquely decodable code. Because at some point, we are going to confuse S2 for S4 when decoding.
Yeah.
Is that okay?
Yeah.
Okay. Now, we now have code D, which is sigma I equal to 1 to 4, 2 to the Li, which is 1 over 2 to the power of 1, plus 1 over 2 to the power of 3, plus 1 over 2 to the power of 3, plus 1 over 2 to the power of 3. Is 1 over 2 plus 1 over 8, plus 1 over 8, plus 1 over 8. And that will give us what? Now, this is going to give us 7/8, which is less than 1. And it means, now when we look at this, it is prefix-free. No code is a prefix of another, so we can say this is uniquely decodable. Okay, now that we have been able to establish codes that are uniquely decodable, prefix-free, so we now know how to represent our source symbols when if we have to transmit from the source. Now, how do we compress these symbols? So let's look at a few algorithms, the simple ones at that. So let's look at source coding algorithms. Okay, so now we have quite a number of source coding algorithms. We have Huffman coding. So we say this is a variable length encoding algorithm that assigns shorter codes to more frequent symbols. So we're going to see how this works. And longer codes to less frequent symbols. So it means if we have A, B, C, D, E, for instance. So, well, how many was the length? Are we going to assign 0, 0, 1, 0? Oh, sorry. Are we going to assign 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, then what now? What do I assign to this? So I don't get a prefix. I'm stuck. Okay, so already assigned 1, 0 here. So okay, I'll leave this so I don't waste much of our time. So now, how do we map this? So I assign 2, I assign 3, I assign 3, I assign 4. So how are we going to do that? So we are saying that the Huffman code actually is a variable length encoding algorithm that assigns shorter code lengths to more frequent symbols. We'll see how that works. We'll play with an example. And then it assigns longer codes to less frequent symbols. Then we have another source coding algorithm, the Lempel Ziv. Think as Dutch, they pronounce W as V, Verch. So LZW. So this is more like a dictionary-based compression algorithm, okay? Okay, so here it literally replaces repeated occurrences of data with references to a previously encountered sequence. And by so doing, it reduces redundancy. Okay. So that's how this algorithm works. It's a very interesting algorithm. You may also want to look up, okay? Then another source coding algorithm is the arithmetic coding. And one way you could even play with things like this, you could try to compare the impact of all of these codes to source coding by looking up a comparative analysis, okay? So you just go to your MATLAB coding and try to run a comparative analysis of all of these codes to see which is more efficient, Okay, so with that, you are done with your assignment. It's just one trick. So for the arithmetic coding algorithm, the algorithm literally maps a string of symbol into a single floating point number, and in that defined interval. So it's literally capable of achieving higher compression ratios compared to Huffman. Okay, so this is more efficient than Huffman. Okay. So, but when we talk about complexity, it is more computationally expensive. Okay. Then we also have the run length encoding. Run length encoding. Okay, such that it's one in which a simple form of data compression in which the sequences of the same data value are stored as a single data value, and then you count, rather than just leaving it as the original sequence. So it's one interesting algorithm as well. Then we have the Burrows-Wheeler transform. So we say it's a reversible transformation that literally rearranges the character in a string to improve compressibility. Here, how do I place this now? It often utilizes this pre-processing step in processing algorithm, and then another source coding algorithm is predictive coding. So this approach predicts the value of the current symbol based on previous encoded symbols. And then it encodes the difference between the predicted and the actual. So it's more like exploiting or exploring temporal redundancy. Okay, so it's more like a predictive system. So what the predicted code then matches with the previous, then is able to match to ensure that compression technique. There are quite a number of them, okay? But for us to see how this works, we also have the Elias code, okay? So we just compare two, okay? So we have Huffman, we have the Shannon-Fano scheme, okay? That's another interesting algorithm, okay? So now I'll just try to play with the simple ones, okay? We'll play with the simple one. So let's look up the Shannon-Fano and the Elias code, the Huffman code. So let's look up Huffman. Okay. Now, when we talk about the Huffman, so I'll compare Huffman and Elias. So we'll see how they differ. Now we know Huffman is an optimal code in that its efficiency approaches unity. Okay. So if, for instance, we want to apply the Huffman code, how does the algorithm work? Now the algorithm operates in two folds. Okay. It performs reduction, then it performs splitting. Okay. So the algorithm is actually used for the construction of optimal shortest expected length prefix-free codes. Okay. Now, in this algorithm, when we talk about the reduction, the first thing is to list the source symbols in order of reducing probabilities. Okay. So let us assume we have these symbols. So let's change the color. We have the symbols. A, B, C, D, E. So let's assume this is the probability distribution, and then we have the code words, right? So for this, so let's say the probability is 0.4, and this is 0.19, then this is 0.16, and this is 0.16, then we have 0.15, then we have 0.1. So here the code word for this is 1, then this is 000, then this is 001, and this is 010, and then this is 011. So how this algorithm works is such that at first, it lists the source symbols in order of decreasing probabilities, okay? So we look this up. So from the highest to the lowest. So let us do that. Well, it has been done for us. So let's assume it wasn't done that way. Then we'll have to do that. So we'll move from 0.4, 0.19, 0.16, 0.15, then 0.1. Did you get that first point? We are still in reduction, right? So the first point is that it lists the source symbols in order of decreasing probabilities. Then after that, it reduces the two least probable symbols to one symbol with probability. So if we now add these two together, so once it adds these two together, what are we going to get? That will be 0.25. So once it does that, then it will now reorder in order of decreasing probability. 0.25 is larger than 0.19. So it's going to come to that point. So it's going to be here now, 0.25. So this maintains 0.4. So it means this is now going to come under, which is 0.19. And then this is going to come under on this line, 0.16. So we have reordered again, right? Then it's going to continue to repeat this reduction step until only two symbols remain. So we now have to reorder again. So we can add these two together. So what are we going to get? 0.19 plus 0.16, that should give us 0.35. So that's still larger than 0.25. So it's going to come here, 0.35. So we reorder, this is still the largest, which is 0.4. Then this now comes under, which is 0.25. Then we now have to add this again. 0.35 plus 0.25 is 0.6. So that becomes the largest. So we arrange in order of decreasing probability 0.6. And this comes here 0.4. And once we add these two together, it's going to give us 1. So we are done. So the probability is 1. So it means the probability distribution is equally correct. Now the probability distribution cannot exceed 1 for the occurrences. So we are done with the reduction step. So the next point is to split, okay? And for us to split, then it means that we now want to begin to assign 0 and 1 to the two final symbols and work backward. So here, so I want to use different colors this time so we don't confuse things. So it means we are going to assign 0 to this and 1 to this. Okay? So now we are going to work backward. So by the time we add 1 to this, we realize that 0.4 is still the same. So this is going to be 1, right? So we're going to assign 1 to this still because it's still the same 1. So if we trace backward, this is still 1. And we trace backward, it is still 1. So it means 0.1, it will be assigned just 1 bit in this Huffman coding. Is that clear? Is that clear, please?
Yes, sir.
Okay. Now, we see that this 0 traces to this point and it terminates here. So we are going to repeat the 0 on both sides. But this is a new step. So we're not going to add another 0, 1. So let me change the color to something else. So we know here we are not adding 0, 1. Okay. So we now see that this 0.25 is the same as this. So we're going to assign the 0, 1 is the same, 0, and then 1. That's the same, right? And if we trace backward, so we still have that 0, 1 here, right? That's 0. So let's just do that. So we know, okay, let's wait. Let's not do that yet. That's another step. So, but the point is, we've now assigned this, right? So we've traced this backward. That's that. So this 0, 1 comes to this 0.35. So it means this 2 points, we now have 0, 1, because we are now assigning 0, 1, then we expand or lengthen the code to cope with the successive split at each stage. We distinguish between the two splits system by adding another 0, 1. So that's what we are doing. So it means that we've taken care of this, but this point traces to this point. So we have 0, 0, 0, 0, 1. So we have 0, 0. Then we have 0, 1. But since it's a new step, we are now going to add another 0, 1. So we have 0, 1, right? Is that clear? And now we see that all of these two, they are similar to this. So it means this 0.19, 0.16, we have the same bits with all of 0.19, 0.16. So we just repeat that here. So that's 0, 0. So I want to be consistent with the colors. 0, 1. And then which other color did we use? Green, right? 0, 1. But at this point, we see that this for 0.25, so it's connected to this branch. So it means we have 0, 1, then we are going to add another 0, 1 to it. So let us repeat what we've got. What comes down? 0, 1, 0, 1 comes down, right? Okay, so let's maintain the same color. So now we are going to assign 0, 1 to it again. Boom, we are good. So in this case, we've been able to assign. Okay, go ahead, please.
For 0.35, when you bring it down, it's supposed to be 0, 0, 0, 0 first, then 0, 1, 0, 1.
Ooh,
so that means
yeah.
0.06 is supposed to be 0, 0,
Yeah,
1.
you're right. You're right. You're right. 0, 0 is now 0, 0 comes down 0, 0, 0, 0, then 0, 1. So this would be 0, 0. Yeah, thanks for the observation. That would be 0, 0, 0, 0, 0, 1. Yeah, it's correct now. That's what it should be. Yeah. So thanks for the observation. Now that we have done this, so it means that our distribution for A, 0.4, we have 1B, right? For 0.19, we have 0, 0, 0. We have 0, 0, 1, 0, 1, 0, 0, 1, 1. So I already wrote it here, okay? So we generated it. So from the beginning, this weren't supposed to be here, right? We're only given the probabilities, isn't it? Okay? So the idea is that we're given the probabilities, and then we had to work it out, for which this is 1, this is 0, 0, 0, this is 0, 0, 1, then this is 0, 1, 0, then this is 0, 1, 1. Yeah. So the next thing to do is to estimate the expected length and the entropy, and then we'll not check for the efficiency of the code. Now the expected length, L of C, is the same as the expected value of the length. And now we already know the probability is 0.4 and the length is 1. So we have 0.4 times 1 plus 0.19 times 3 plus 0.16 times 3, that's the length, plus 0.15 times 3 plus 0.1 times 3. So this should give us 2.2 bits per symbol. And then the entropy, h of x, will be the same as the expected value, negative of the expected value, p of x, log p of x, right? So this is going to give us negative 0.4 log 0.4 minus 0.19 log 0.19 minus 0.16 log 0.16 minus 0.15 log 0.15 minus 0.1 log 0.1. So now you know that this is in base 2, so you have to do base conversion by taking log 0.4 base 10 divided by log 2 base 10, then you multiply by 0.4, and you're going to get in all 2.15 bits per symbol. So the efficiency of this code, like we mentioned earlier, will be the entropy over the expected length, which will be 2.15 divided by 2.2. And this will give us 97.7%. Okay. So for the Hoffman code, this is what we get, 97.7%. So now let us try Elias code or Shannon-Fano code to see if we will achieve up to this. But based on the symbols and the probability of occurrences, we've been able to use the Hoffman code to generate the code word for each symbol. Is that clear?
Yes, sir.
So now let us try another algorithm, the Shannon-Fano Elias coding. Now, this algorithm literally utilizes the cumulative distribution function to allot code words. So in this case, we'll play with the same example where we have the symbols A, B, no, let's give some space this time. So we have the probability of occurrence here, 0.4, 0.19, 0.16, 0.15, 0.1. So we need to figure out the code word, right? Now, for the Shannon-Fano Elias coding, the first thing to do is also to list the symbols in order of decreasing probability. So that has been done for us. So we have 0.4, 0.19, 0.16, then we have 0.15, then 0.1. Then we partition. Now, we do this by partitioning. So in this case, we are going to partition the set into two sets that are as close to equiprobable as possible. And then we assign 0 to the upper set and 1 to the lower set. So we're now going to look at this. So for us to be able to divide this into two sets that are equiprobable, what do? So this is 0.4. Now, if we should add 0.4 to 0.19, that would be 0.59. So we're now having 0.59. Then if we add, this is 0.25 plus 0.16, that will give us what? 0.26 plus 15 plus 16.
0.41.
This is 0.41. 0.41. Now, is that close? Now, let us check another partitioning. So we know which is better. Okay. Now, if we take 0.4 to be on its own and add all of these, that would be 0.6. I think this disparity is too much, right? So we can go with this, isn't it? Yeah? Hello? Are you with me?
Yes, sir.
So it means we can divide this into 2 equal parts. So once we divide this into 2 equal parts, so this is our first division. So what the algorithm says, assign zeros to the upper part and 1 to the lower part. We have done the first division, okay? So we'll close this deal. So then we now have 2 partitions, and we can literally divide the upper part into 2 because that's all we get. That's all we've got. So this will now be 0, 1, right? But how about this part? Now, if we should split 0.16 and then 0.25, this is 1, or better still 0.16 plus 0.15, that is 0.31 and 0.1. So this is too far. So we want to take this, right? So we can split this into 2 equal halves. We assign 0 to the upper half and 1 to the lower half. And now for the lower part, we have just one more option. We can split this and say 0, 1. So that ends our partitioning. There's nothing to partition again, right? Is that clear?
Yes, sir.
Then it means that 0.4 has 0, 0 code word. 0.19 has 0, 1. 0.16 has 1, 0. Then 0.15 is 110, and 0.1 is 111. So we've been able to generate the code word for the symbols given the probability distribution. So the next thing to do, we already know our entropy is 2.15 as estimated earlier, bits per symbol. But we know that the expected length is going to vary this time. So let us compute the expected length for this case. So the expected length, L of C, will be P sub I, S sub I, which will be 0.4 times 2 plus 0.19 times 2, that's the bit length, plus 0.16 times 2 again, plus 0.15 times 1 to 3, 3, plus 0.1 times 3. So once we perform this operation, we now have the length to be 2.25 bits per symbol. So what's going to be the efficiency of this code? The efficiency, once again, will be the same as h of x divided by the expected length, which will be 2.15 divided by 2.25, and that will be 95.6%. So with Shannon Fano, we got this, but what did we get with Elias? With Hoffman, rather. Hoffman gave us what?
97 points.
97.7.
97.7.
97.7.
0.7%. So you see that Hoffman is more efficient in terms of developing the code words for the same set of symbols given the probability distribution. So this is one way of achieving source coding, okay? So that we don't just assign arbitrary bit strings to some code words, okay? Is this okay? So now I think I will just mention this. We've tried to describe 2 major concepts: the expected length and then, oh, sorry for that. Let's use a straight line. Expected length and entropy. Now, the expected length is also the average code word length. we need to take note of that. Okay, this is average code word length. Okay, so we can literally say it is the average number of bits required to encode each symbol from the source using a specific encoding algorithm from what we have seen. While the entropy provides the theoretical lower bound on the average code word length. So while we are dealing with the actual, the entropy gives us the theoretical limit. Okay, so in other words, the expected length provides the actual average code word length. Produced by the encoding algorithm. Okay, so that the entropy tells us the minimum average number of bits needed to encode each symbol from the source. Okay, so I think I felt I should mention that. Okay, and now one more thing is wrong code. So in wrong code, the expected number of the expected length under the probability distribution of the code assignment, say L of X, is given as log 1 over Q of X. And this satisfies what we talked about earlier, the entropy plus the relative entropy. And this must be less than the expected value of the expected length, which is also less than, okay, less than h of p plus the relative entropy between this plus 1. And you will recall from what we said earlier that if the wrong code is used for a distribution, is say Q of X in this case, then we would need h of p plus the relative entropy bits on the average to describe that random variable. Because we want to tell the entropy of the true distribution and the divergence between the true and the wrong distribution. So once we have this, we now have h of p plus the relative entropy between p and q bits to describe that random variable. Okay, so I just felt I should also mention this. Okay, so at this point, we have just a few minutes. So do we have any question right now? Do we have any question? Before we call it a day. Any comment? And before we leave, you may want to leave your details in the chat room, probably your name, your matric number, and so we are able to keep track of the class attendance, okay? So for now, any question, please? We have Mr. Ezekiel Anuge, right? Rachel Mama, Ibrahim Rahim.
That's correct.
Yeah, so do you have any comment, any question? We have a Blessing Enoma, Richard Irabo. Any question, please? Victor, we have Victor, right? We have Victor.
Actually, sir, I actually got kicked out of the class for some minutes, so I
Okay.
probably look up for the video.
Okay, okay. So I'll try to upload this as soon as possible. Okay, so I think we seem to be good, right? Someone wants to say something, Richard Mama?
No, I'm fine, sir. Thank you.
Okay, okay. Okay, so for now, I think we'll call it a day and hope to see you in our next class. So bye for now.
All right, sir.
Thank you.
All right, sir. Thank you.
Thank you, sir.
Thank you, sir.
You're welcome.